In this tutorial, we're going to talk about rational functions. And a rational function can always be written in the form of some function n of x divided by some different function, we'll call it d of x. N for numerator, d for denominator. And in general, the domain of rational functions is all real numbers except for where the denominator is 0. That actually happens to produce asymptotes, which we'll look at later. So let's take a quick look at an example of this, and I'll show you what we mean. So the function f of x equals 2 over x plus 1 is a rational function, and what we're going to do is figure out where the denominator is equal to 0. And in order to do that, you just simply set this aside and set it equal to 0 and solve. And when I do that, I subtract 1 from both sides, and that gives me x equals -1. Now, there's a particular way in which we can actually write this domain out. There's actually a couple different ways. The way that I'm going to show you is called set builder notation, and it is a little bit more complex, but it's much more efficient and much more formal. So here's what we're going to do. I'm going to say domain, and then 2 dots, and then we use a curly bracket. And the first thing that we're going to do is we're going to state the variable upon which we're talking about, which is x. And then we create a vertical bar after that, and this, you pronounce that vertical bar as such that. So far the domain is my x values such that. And now we're going to tell our reader what a domain is. And the first thing that we're going to do is we're going to say that x is all real numbers, right? Except for when it's 0. So the way to say x is all real numbers is we say x, and then we do this little backwards C with a bar, and it just means is an element of, or it's in, or it's a part of, like that. Real numbers is denoted as 2 double barred and then an R. So this reads so far, the whole thing, x such that x is an element of all real numbers, and then we do comma, and now we're going to tell the reader the 1x value or 2 or 3x values where this doesn't work. So we're going to say x is not equal to -1. And then we close our curly bracket. And this will take a little bit of practice to get used to. So if you don't get it right the first time, it's fine. I'm going to use this throughout the entire video today. So just keep trying. So let's talk about the asymptotes of our rational functions. So our vertical asymptotes will always have the equation x equals, and then wherever it passes through the x-intercept. And our horizontal asymptotes will always have the equation of y equals, and then wherever it intercepts the y-axis. So, for example, a vertical asymptote would be something that looks like this. So it's like an imaginary line that your function will run along a side with. So something like this, where it's not going to pass, and like this. And it also will not pass that imaginary vertical line. And for horizontal asymptotes, it would be something like this, and the difference between horizontal asymptotes and vertical asymptotes is that you can actually have a function that passes through a horizontal asymptote. Something like this. It would be like this, and then just follow it forever. So there's a few different examples of functions that don't pass at horizontal asymptotes, and there are some that do. So where do vertical asymptotes happen in our equation when we have our f of x equals n of x over d of x? Which parts give us vertical asymptotes? And I already told you just a minute ago that our vertical asymptotes happen when d of x is 0. So we're going to go ahead and make a note of this. So when d of x equals 0, just like that. And my horizontal asymptotes are a little bit different. Our horizontal asymptotes is when we compare the degrees of our numerator and denominator. So for example, we only take a look at the leading term of either the numerator and denominator when doing this. And we're going to call the numerator's leading exponent or leading degree n, this guy right here, and the denominator's leading exponent or degree as m. So a few different things will happen based upon those degrees that will help us determine where our horizontal asymptotes are. And the first rule is if n ever happens to be smaller than m, then we have our horizontal asymptote happening at the line y equals 0. And this is true every time, as long as the numerator's degree is less than the denominator's degree. If n ever equals m, so in other words their degrees are the same, then we write their horizontal asymptote as the line of the ratio of their coefficients. So for example, if you take a look up here, let's say that we have a function ax cubed divided by something bx cubed. And we've got more stuff here added on, but we only take a look at the leading terms. And a and b, of course, represent real numbers. So the only thing that you have to do with that is take your a and divide it by your b, and that reduced is where your horizontal asymptote is, as long as those degrees are the same. And the last case is if your leading degree for the numerator is larger than that of the denominators, and that is that there is no horizontal asymptote. It doesn't exist. It's just going to be a nice fluid function, unless there's a vertical asymptote, of course. So that's how we determine our horizontal and vertical asymptotes. So let's put this into practice by taking a look at an example. We're going to find the horizontal asymptotes and vertical asymptotes for this function. And typically what we're going to always have to do is factor. It's just going to be a part of what we do for rational functions. So when we factor the numerator here, we're going to have x and an x, factors of 2 that yield a 1x here. That's going to be a 2 and a 1. And it looks like we're going to need a positive 2 and a negative 1 to come up with the positive 1. And in the denominator we have x, and I need factors of 6 that give me a 1. That's going to be 3 and 2, and it needs to be negative. So negative 3 and then plus 2 will give me a negative 1, which is what I have right here. So anything that they have in common we're going to ignore for now, so the x plus 2's will cancel. So I'm going to take a look at where my denominator is equal to 0, which is going to be this part right here. So x minus 3, and I'm going to set that equal to 0. So add 3 to both sides, and x equals 3 is my vertical asymptote. So the next thing that we're going to do is compare our leading terms. So back to the original function, I have x squared right here, which is 1x squared, and I also have 1x squared down here as well. So what I'm going to do is I'm going to compare their exponents to see if they're different. So I've got 2 compared to 2, and they're the same. So this is going to follow the rule where n is equal to m. And when that happens, I just set their ratio of the coefficients, a over b, which in this case is going to be 1 over 1, which of course is equal to 1. So how do we write our equation for this? Well, horizontal asymptotes get the y equals equations. So, oops, not v. So horizontal asymptote happens when y is equal to 1. So that's how we're going to find our horizontal and vertical asymptotes. All right, and the last function, or the last example that we're going to take a look for now, is to sketch the graph of f of x equals x squared minus 9 divided by x squared minus 2x minus 3. And so we want to look for a few things when sketching these by hand, and we try to take a look at 4 main things every time. we try to look for the y-intercept, the x-intercept, and our vertical and horizontal asymptotes. Once we have those things, our function will always follow the pattern of our parent function, which, in case you forgot, the parent function for this is 1 over x, which always looks like this. Okay, so that's just the general form of what we're looking at. So before we go into those numbers, we have to factor our original function. So x squared minus 9, that's a difference of perfect squares. That's going to become x plus 3, x minus 3. Our denominator, when factored, is going to become x minus 3, x plus 1. So the first thing that we do when we do this is we're going to find the y-intercept first. And the y-intercept happens when our x is 0. So I'm going to plug in 0 for our function, and this does not require the factored form necessarily. We can actually plug in 0 into the original, but we have to get it factored first. So when I plug in 0 into the original function, I get 0 squared, which is 0, minus 9, and then we have 0 minus 0 minus 3, and all this becomes negative 9 divided by negative 3, which is reduced to positive 3. So I'm going to mark that on my graph. So I'm going to find 3 on the y-axis, and I have my first point. And I'm going to then go ahead and do my x-intercept. And the x-intercept comes from the numerator of our factored form. So if you'll look right up here, please understand that x minus 3 is repeated in the numerator and denominator, and something special will happen with that. Any of the parts that are repeated in the numerator and denominator we ignore when finding our y and x intercepts. So the x-intercept is when the numerator's parts that are not repeated in the denominator are set equal to 0, which in this case is just the x plus 3. So we set that equal to 0, and we solve that, and we get x equals negative 3. Remember, something else special happens where the factors are repeated. So I'm going to find x equals negative 3, which is right here, and now we've got 2 points that we have. So far, so good. The next thing that we're going to do is find the vertical asymptotes. So vertical asymptotes happen when the denominator is 0, of course, not with one of the repeated factors. So this is just going to be when x plus 1 is equal to 0, which I work that out and I get x equals negative 1. So I'm going to go in here and carefully create my imaginary vertical line that goes through negative 1 on the y-axis. And last but not least, of course, we're going to do the horizontal asymptote. And the horizontal asymptote happens when we compare the degrees. So in the original function, my leading degree is 2 in the numerator and 2 in the denominator. And of course, since n is equal to m, my horizontal asymptote will happen at the ratio of their coefficients, which is 1 over 1 yet again. So this is going to be y equals 1. So I'm going to find that on my on my y-axis and make my imaginary line there as well. So what's the special case that we were talking about earlier when I have repeated factors x minus 3 and x minus 3? This actually creates a different set of points, which are holes. And these are very interesting points in a rational function when we talk about like applications and whatnot. But what we do for holes is the parts that they have repeated, we do set that equal to 0. So this is the repeated part. I set that equal to 0, and I get x equals positive 3. So at this x value that we have, we're going to have an open hole. Just like when we have inequalities where a value is excluded and we make an open circle, it's going to be the same thing here. So what I'm going to do to figure out exactly where this is happening is I'm going to plug this in to my graph, and when I do that, I actually get 0 divided by 0. This is what we call indeterminate. And you think just, dividing by 0 is bad enough in math? This is worse. This is like there's absolutely nothing happening. We can't determine anything. So wherever x is equal to 3, I'm going to just have an open circle there. And we're just going to kind of estimate where that might be. And since I know that my function is positive and it looks like my parent, I know that 3 comma something is going to happen somewhere up here. Okay, so I'm just going to have my open circle there. And I am finally ready to go ahead and connect all of my points together and get my function. So I'm going to start from the left, and I need to pass through my x-intercept there and then follow my asymptotes. Just like that. When I pick it up on the other side, I'm going to start again from the left, so up here on top, and I follow through my y-intercept, and when I get to my hole, I'm going to stop and lift up my pen and continue from the other side, just like that. So that is how we're going to sketch our graphs of rational functions. And that will conclude this tutorial.